Hello, my name is Shimin Chen. I'm from Institute of Computing Technology, Chinese Academy of Sciences. Today, I'm going to talk about progressive join algorithms considering user preference. This is joint work with Mengsu, my student, and Nantia Makrynioti and Stefan Manegold at CWI. Progressive query processing is a new attractive paradigm for exploratory data analysis. In this work, we consider the case where users want to progressively see join results which are ordered according to user preference. This figure shows a two-way join between tables L and R. We consider the case where user preference can be described by certain columns in the input tables. For example, such columns could be greetings, discount, price, and so on, or some combination that reflects user preference. Without loss of generality, column X and Y in the figure give preference values normalized to 0 to 1 range. We follow previous work to mainly consider the case where input tables are sorted by preference values. To compute the preference of the join results, we can use a linear function, which is the most popular preference combining function. Please see discussion about other combining functions and how to support unordered inputs in the paper. Our goal is to achieve both fast early results and fast full results. There are two types of existing solutions. The first is the blocking approach. Basically, it performs a blocking join, then sorts the results according to user preference. The problem is that join sort does not generate results progressively. There is no early result. The second approach is to extend existing top K join algorithms. Given a pre-specified K, a top K join returns the first K join results according to user preference. For example, rank join performs a symmetric hash join on the two input tables. It puts the join results into a priority queue of size k, then computes a bound to determine if the result can be safely returned to the user. However, if we extend rank join to progressively compute all join results, rank join will take a really long time. It incurs very significant sorting overhead. We would like to reduce or even eliminate the sorting overhead. Let's consider the space of preference values of join results. The horizontal axis shows the preference values of table L. The vertical axis shows the preference values of table R. A point in the middle represents a potential join result. Its preference value is computed as fxy. Given any preference combining function, we can obtain the contour lines in this space. The points on a contour line have the same preference value. For example, the contour lines for the linear function are diagonal lines. The space between two contour lines contain previous scores in the same score range. We call this a contour range. As contour lines go forward from bottom left to top right, the results preference score range decreases. We divide the axis into equal-sized intervals and set the x interval and y interval sizes based on parameter a and b, so that x interval and y interval contribute similarly to the join result preference score. Then the join results of the two intervals are in a rectangle in the result space. The rectangle spans only two contour ranges as shown in the figure. We exploit the contour lines to reduce sorting cost. We propose several variants of contour joins. In the first algorithm, we perform symmetric hash join on tables L and R. Here, 0, 1, 2 correspond to the x interval and y interval in the previous figure. In each iteration, we process an interval LL tuples and an interval of R tuples. We put the join results into a set of buffers. Each buffer corresponds to a contour range in the previous figure. For example, buffer 0 corresponds to the bottom left contour range with highest preference. Buffer 1 corresponds to the second contour range, so on and so forth. We put a join result to the buffer that it belongs to. In this way, we avoid sorting across buffers because the buffers are already ordered according to user preference. We only need to sort the results within a buffer. We can output the results in the buffer if the lowest preference score of the buffer is greater than the highest preference score of results in the current iteration of the symmetric hash join. In the second algorithm, we make sure both inputs and outputs follow contour lines. In step 0, we compute the join between R0 and L0. In step 1, we compute the join between R0 and L1 and the join between R1 and L0. In step 2, we join the three rectangles. We see that the join results of a step spans two contour ranges. Two subsequent steps overlaps a contour range, but step 0 and 2 do not have any overlaps. In this way, we only need two buffers to hold the join result. Compared to the first algorithm CJPI, the CJPB algorithm reduces the intermediate result size, leading to better CPU cache behavior. However, it may perform a larger number of small joins for the small rectangles. In real-world applications, there are cases where the exact preference order among similar results might not matter so much. So we can relax the sorting precision by allowing a small error in the order. If this is the case, we can judiciously choose the input intervals to further remove intra-buffer sorting. We apply relaxation to the two precise algorithms and obtain two relaxed algorithms. Here P or R stand for precise or relaxed. I or B stand for input or both. And we have four variants of contour joins: CJPI, CJPB, CJRI, and CJRB. In the experiments, we generate datasets based on TPCH table's line item and part sub. The preference values are based on L discount and PS avail quantity columns. We normalize the preference values. We generate three datasets to fix the input size while increasing the join output size. The second dataset fixes the output size while increasing the input size, and the third dataset increases both the input and the output size. In this way, we can vary the fraction of time spent in join and in sorting and observe the behavior of different join algorithms. We perform experiments while varying scale factors in each dataset and varying the preference companion functions. Overall, we see that compared to rank join, we achieve much better performance for generating both early results and full results. Compared to the blocking join sort, we achieve comparable or better performance for generating full results. We look at one set of results in more detail. Here we fix the input size while increasing the join result size 64 times. The left figures show the percentage of results generated over time. The right figures show the breakdown of total execution time into join time and sorting time. We see that as join result size increases, the fraction of sorting time increases, and the rank join becomes very poor because of the sorting overhead. On the other hand, contour join significantly reduces the sorting overhead, and the CJRB is the best performing algorithm. In conclusion, we study preference-aware joins in the context of progressive query processing. We propose to exploit contour lines in the join result space to reduce sorting overhead. Our experimental results show that contour join is a promising solution. Thank you.